Welcome back everyone to this lecture on the theory and intuition behind KNN classification. KNN, or k-nearest neighbors, is one of the simplest machine learning algorithms. The way it works is it simply assigns a label to new data based on the distance between the old historical labeled data and the new incoming data. Let's go through the intuition behind k-nearest neighbors with an example use case. Sexing newborn chicks as either male or female is still a very manual process, and you can check out the full details behind this on the Wikipedia page for chick sexing. Let's imagine that we happen to gather a data set of baby chick heights and weights, and then we had someone check out those same chicks and actually label them as male or female. How could we train a machine learning algorithm to identify the sex of a new baby chick based off these labeled historical features? So we're going to imagine we have this height and weight data set, and what we do is after marking down the height and weight of all these chicks, we have someone who already has the experience of sexing baby chicks, and it assigns these chicks as either male or female. So we have our historical labeled training data here. Now the question is, you have a new baby chick coming down the line, and you've marked down its height and its weight, and it happened to land right here on this two-dimensional chart. How would we assign the sex to this new point? Intuitively, you can probably already know that this point is likely to be female, because you can see that it tends to have similar patterns of weight and height as the female chicks do. And this intuition, quantitatively, really comes from the distance to the historical labeled points. All you're doing in your mind is you're checking out what points is this new point closest to. But what happens when we're dealing with a less obvious point, one that kind of lies between class 1 and class 2 here, or male versus female? Also, how many points should you be considering? You saw here that we drew a line from the new point to 3 historical points, or k is equal to 3. But if you're dealing with a less obvious point, how do you decide on the right number of points to consider? So let's go ahead and imagine a situation that looks like this. We have 3 female points that are historically labeled, and 6 male points that are historically labeled. And now we have a new point which we would like to classify as male or female that's lying right in between both groups. If you set k is equal to 1, this is the simplest possible version of k-nearest neighbors. Essentially, you're just saying is find the closest historical labeled point to this new incoming data point and then assign it to the same label. So you would keep this new point then as female. If you set k is equal to 2, now you're saying is check out the 2 closest points to this new point. And in this case, we would keep that female assignment. Now with k is equal to 3, you'll notice we're actually beginning to picking up connections to male. So now we have 2 female historical points and 1 male point. And the way this works with k-nearest neighbors is you're essentially taking the majority class here. So you have 2 female points versus 1 male point. So in a sense, you have more votes, so to speak, for the female class. So the algorithm would decide to label the new point as female. But what happens in the case of something like k is equal to 4? You'll notice k is equal to 4 actually leads to a tie. You have 2 votes for the female class and 2 votes for the male class. What considerations do we have to make in the case of a possible tie? There's actually many different options for how to break ties. One way in the case of binary classification is to simply just choose an odd number for k. If you have only 2 classes and you have an odd number of k, then you'll never have a tie. Another method is, in the case of a tie, simply keep reducing k by 1 until the tie is broken. You could also choose to simply randomly break the tie. In the case of a tie, randomly choose one of the classes. Or, finally, you could choose the nearest class point. So, in the case of k being equal to 4 being a tie, you would simply reduce all the way back down to k is equal to 1 and choose the nearest point as your assignment. The obvious question is, what does scikit-learn do in the case of a tie? If you check out the documentation, it actually has a warning that regarding the nearest neighbors algorithms, if it's found that 2 neighbors, neighbor k plus 1 and neighbor k, have identical distances but different labels, the results will depend on the ordering of the training data. And that means, if you take a look at the source code for scikit-learn, in the case of ties, the answer will be the class that happens to appear first in the set of neighbors. And the ordering that is done by scikit-learn means that they're ordered by distance. So it chooses the class of the closest point. Essentially, the last consideration option we had. If you have a tie, simply choose the nearest point. So here we have k is equal to 4. And you can see that we're simply going to choose the closest k value. So k is equal to 5 could cause a switch from previous k values. You'll notice that as we increase k, we're actually more likely to hit up on more male points than we are on female points. So what do we do in this case? Are we okay with just expanding k? Is that going to lead us to a more accurate algorithm? What we need to do is figure out, how do we actually choose the best value of k? We just saw that as we increase k, we have the issue of a possible tie, which we know how to fix now, but we still have the issue of trying to figure out what is the optimal value of k. What we want really is a k value that minimizes the error, where you can define error as simply 1 minus accuracy. So if your algorithm seeks to be 90% accurate, that means you have a 10% error. The two methods we can do are a more manual method known as the elbow method, or you can simply use cross-validation to do a grid search of multiple k values and choose the k value that results in the lowest error, otherwise known as the highest accuracy. Let's first go through an explanation of the more manual elbow method. The way elbow methods work in general is you're going to train a model with multiple k values on the same set of training points. And then you're going to test all these models that are using different k values on the same test set. And what you're going to do is you're going to mark down the error rate for each k value. And typically what you see, not always, it depends on the data set, is at the start, when you begin to increase k, you're gathering more signal from your training data points. So you will see a sharp reduction in the error rate. But eventually, for most data sets, you get this elbow point, where as you begin to increase k, somewhere around the range of, let's say, k is equal to 10 on this plot, we can see we're really not reducing the error rate that much. Past this value of k, you're only beginning to reduce the error rate by about 1%. And this is where a human data scientist can make the decision whether or not to vastly increase a k for a small reduction in error. You're increasing the complexity of your model, and sometimes that may or may not be worth it, depending on the context of your model and your data set. We can tell that for this particular data set and this particular chart, it looks like a k value of somewhere in between k is equal to 20 and k is equal to 25 actually has the lowest error rate. But it didn't actually decrease the error rate that much compared to a much smaller k value of somewhere like k is equal to 8. It's up to the human to actually have some discrepancy over whether or not they want to choose a much larger k value. In general, because of this human discrepancy that could occur with the elbow method, we would recommend that you simply use cross-validation to figure out the best value of k. You can use cross-validation in combination with a grid search of multiple k values. And in this case, this cross-validation is only going to take into account the k value with the lowest error rate across multiple folds. However, this could result in a more complex model. For example, it could choose a higher value of k if that particular k happened to be the optimal k that minimized the error across multiple cross-validation folds. You should consider the context of the problem to decide whether or not the larger k values are an issue. So in general, the way the k nearest neighbors algorithm works is you're going to choose a k value based off either the elbow method or cross-validation. And then once you have that k value, to actually implement k nearest neighbors, it simply is going to sort the feature vectors, that is the vectors in an n-dimensional space, n dimensions being equal to the number of features you have, and then it's going to sort them based off some distance metric to the new point you want to label. Something to note here is that this actual time to label a new point requires you to sort all the points all over again based off the distance to the new incoming point. So in theory, this could take a while depending on how fast the computer is and how many points you actually have. But then what you're going to do is once you've sorted the feature vectors by a distance metric to the new incoming point, you'll simply choose the class based off the k nearest feature vectors and the votes tallied up per class. The last consideration you need to make is how you're actually measuring the distance between the old points that are labeled to the new unlabeled point. And keep in mind, there's many ways to actually measure distance. There's many formulas such as Minkowski or Euclidean or Manhattan distance that you could choose in order to figure out the distance from one point to the other. Another consideration you should make for k nearest neighbors is should you scale the distance? In general, you should consider that features could have vastly different value ranges. Here we can see that these points are very far apart along features 1, but very close together along feature 2. So you can see again, distance of feature 1, these points are far apart, but if you were to take a look at just feature 2, it looks like they're almost the same values. So depending on what distance metric you're actually looking at, this distance of scale between feature 1 versus feature 2 could cause some issues. So in general, what you should always do is scale your data before actually running k-nearest neighbors. So we're going to say that scaling is actually a necessity to run k-nearest neighbors effectively because you're using a distance-based metric. And you don't want a situation like this causing issues with that distance metric. Instead, just don't worry about it by always scaling your features. Okay, while the k-nearest neighbors algorithm is relatively simple, you should always keep in mind the following considerations, which is how you're actually choosing the optimal k-value, either through the elbow method or through cross-validation, and to remember to always scale the features. Let's continue to explore how to perform KNN for classification with Python and scikit-learn in the next lecture. I'll see you there.